Good morning, everybody.
Good morning, sir.
Okay, so let's begin. Can you see the screen?
Yes, sir.
Okay. So in the last class, I think we were talking about this communication subsystem, and we know that essentially, there are two different kinds of transponder, I mean frequency conversion techniques used in the transponder depending on the pair of frequencies which are being used. So if we are using 64 gigahertz bandwidth, then it could be a single stage conversion from 6 gigahertz receiving signal at the satellite to a 4 gigahertz transmitting signal at the satellite. I mean, whatever these hardwares represent, they are all on board the satellite. They are not at the Earth station. And if we opt for the 1411 gigahertz bandwidth, this 1411 gigahertz bandwidth is there, but it has its own problems. I mean, as I had mentioned in the last class, that one of the water vapor absorption lines is around 11 gigahertz, another is around 22 gigahertz. So these water vapor absorption lines, they cause some problems in the satellites signals, in the sense that these microwave signals often suffer from attenuation due to rain. And then again, for the lower frequencies, like suppose the question might arise that why not use 2 gigahertz, like 2 gigahertz maybe uplink and 1 gigahertz downlink. Now those bands, those frequency bands actually suffer very severe, degradation. I mean, very severe disturbances, resulting in rapid and intense and random fluctuations of the amplitude and phase of the signal. So, depending on which layer of the atmosphere we are talking about, whether it is the lower atmosphere extending a few kilometers from the surface of the earth, within which this water vapor related absorption effects are confined, or the upper atmosphere which is ionized, the levels of disturbances are different on the satellite signals, the ionized layer being much more dominant in causing disturbances at frequencies even up to say 2 gigahertz, starting from high frequency, which is around maybe like 50 megahertz or so, going up to 2 gigahertz. Over this entire range of frequency, the ionized part of the atmosphere plays a very important role in causing disturbances to the satellite signals or radio signals. So that's why usually the communication satellites are, kind of their frequencies are allocated starting from around 4 gigahertz or 6 gigahertz. And then again, this frequency pair of frequency around 1411 gigahertz, that once again, suffers from some disturbances which arise as a result of these water vapor related absorption around 11 gigahertz. So, moving ahead, we had also talked about, the fact that because at a particular point of time, at any particular instant of time, there are two frequencies present on board the transponder. So, uh, there is a possibility that, in order to achieve the maximum output power from the transmitting system, we might require the output amplifier to be driven towards saturation level, okay, which is in the nonlinear region. But when that is done, because of the presence of more than one frequency in the transponder, it may so happen that some additional frequencies may be generated, okay, which may cause, problems of intermodulation, and that means some undesired frequency components may be generated. So in order to avoid that, some kind of a balance, some kind of an optimization is done between uh, going for maximum output power and reducing the intermodulation products and maintain linearity of the system. So for that reason, the operating point or the Q point of the output amplifier or transmitter output is usually, downgraded. I should say it is reduced. It is taken. It is moved back to the linear region of operation. There, you maintain the linearity of operation and you have reduced the intermodulation products, but at the same time the maximum output power that is also reduced below its peak value. So this degree to which the transmitted output power is reduced, this is known as the output back off. And we will talk about this TDMA, FDMA, and CDMA techniques towards the end of this course. So typically, this reduction in the output power may be of the order of 3 to 7 dB. Okay, so it is not insignificant. That's what we can understand. That 3 to 7 dB of reduction in the output power is, not very significant, but still it is substantial, particularly when we are talking about signals which are extremely weak, because the transmitted signal when received at the earth station, that is very weak signal and needs a lot of amplification to be done before it could be processed. And the next topic that we will be talking about are the satellite antennas. That means the antennas which are used on board the satellite. Okay, so there are different kinds of amplifiers which are, different kinds of antennas which are used, and we could understand that at the time of launching of the satellite, neither the antennas nor the solar panels, they are, are moved out. So because of that, uh, these are normally folded within the uh, within the body of the spacecraft, which is launching the satellite. And once they reach the altitude of the geostationary satellites, only then they are unfolded and they start their operation immediately after that. So these are the four different kinds of antennas which are normally used on board a satellite. That is, they could either be simple wire antennas, that is monopoles or dipoles. Then they could be like horn antennas or reflector antennas as well as array antennas. So out of these four different kinds of antennas, have you heard the names of these antennas?
Yes, sir.
All of them, all four kinds of antennas?
Yes, sir.
Yes, sir.
Okay. So could you just tell me that suppose this DTH antenna, which we see very frequently on the roof of our building, what kind of antenna are they,
The reflector antenna,
Reflector.
and what is their shape?
the paraboloid. Para-
They are parabolic reflector. And you must have seen that there is one small piece of object which is fixed at a certain distance away from that reflecting surface. So what is
Yes, sir.
that? What is that object?
so
From
that's
that
uh,
yeah. Tell, tell me.
so that is more of a like a waveguide kind of thing, and from there we attach the launching. We attach the coaxial cable from it, and we get either if we are using to launch signal, then we can launch the signal from there, or if we are receiving,
No,
then we
see,
can just
in a DTH we do not transmit anything. We only receive
yes,
signals, right?
yes,
So that is actually the position. That is actually the low noise amplifier, or LNA as it is known as.
okay,
And the low noise amplifier actually converts the incoming, incident radiation into some kind of an electrical signal. That means it has to convert the incoming energy which is associated with a free space wave, and convert that into some kind of an electrical energy which passes through that cable to your television set. Okay,
yes, sir.
because as you can see that this incoming energy or the incoming signal, we cannot see that, okay, that it is coming. But actually when you measure the current or the voltage which is passing through the coaxial cable, you will see there are some finite values. So this conversion from the that free space wave or free space energy into a guided wave through the coaxial cable, that happens because of this particular device, which is some kind of a transducer. It converts the incoming electromagnetic energy to some kind of an electrical energy. And do you have any idea about its location? That means, can I put it anywhere near to the surface of that parabolic reflector, or or do we need to place it at a particular point only? This
Sir, it should be at focus of parabola,
why?
because there it will uh, get the maximum of radiation.
Good. That means this surface of the antenna, which we see as a parabolic reflecting surface, that only acts as a reflector of the incident electromagnetic signal, radio signal. So that is concentrated towards the focus after reflection, that is concentrated or reflected back towards the focus of the parabola. And it is at this location that this LNA should be placed so that it receives the maximum amount of reflection from the surface of the antenna. There will be some losses, of course. I mean, not the 100% of the incident energy is reflected back. Some gets, there are some losses involved, but still, it should be placed, this LNA should be placed at the focus of the parabola, and it converts the incoming electromagnetic energy to some kind of an electrical energy which drives current and produces voltage through that coaxial cable. So, typically, the patterns of the satellite antennas, I mean, we won't go into the details of those different kinds of antennas, their structure, their characteristics, because I think you have already studied them in one of the earlier semesters. So, when we talk about the satellite-based antenna, it is important that for the purpose of communication, we should know the different kinds of patterns and the associated coverage zones that they provide. That means depending on the kind of antenna beam pattern, there will be different kinds of coverages provided. Like for example, in this particular case, as you can see, that this is a global beam. That means from the geostationary altitude, the Earth subtends an angle of 17 degrees. That means from about 36 to 40,000 kilometers above the surface of the Earth, if you look down towards Earth, then you will find that the total angle subtended is 17 degrees. So if it is some kind of a signal which is meant to be received by a large section of the earth, it is not some kind of a particular country-wise transmission broadcast, then one can go for, of course, a global beam, which is having, like, say, for example, 17-degree beam width. And but of course, those who will be doing your projects, perhaps in on antenna, you will understand that a 17-degree beam width is a very big one. Okay, it's not easy to design an antenna with a beam width of 17 degree or so. Then it could be, like for example, spot beams targeted towards maybe two different portions of the earth. Like for example, but of course the overriding condition in all these cases is that in case of spot beams is that the satellite should be visible, radio visible from both these locations towards which the spot beams are directed. Okay, like for example, maybe as I was giving you an example in an earlier class, that the one of the service areas could be towards the Indian subcontinent, that is India, Pakistan, Bangladesh, where more or less, the the Hindi channels, they are more or less, people are familiar with that. Then there could be another one directed towards maybe the Southeast Asia, Singapore, that region. So the location of the satellite has to be such that both these regions, they are radio visible to the satellite antenna. So in that kind of a situation, we can go for spot beams. And of course, you can understand that using spot beams, this is something a little bit similar to what we have already learned about, this frequency reuse. That means spatial beam frequency reuse technique. It is somewhat similar. That means from a particular antenna, you generate different directional beams, and so that you can increase the number of users who are in that particular transmission zone. Then for this phased array antenna, so naturally, the phased array, they have an advantage over conventional single dipole antennas. Just a minute. Okay, sorry. Let's get back to what we were talking about. Okay, so can you hear me?
Yes, sir.
Yes, sir.
Okay, so coming to this phased array antenna, you know that there are several advantages associated with this kind of an antenna compared to a conventional, maybe a dipole or that kind of an antenna. And you could actually, kind of uh, generate the output beam and the output pattern. You could change them by changing the phase difference between two consecutive antennas or two consecutive such sensors, so to say. So, uh, phased array antennas are usually used when when we have a system, a satellite, which is trying to provide communication to multiple regions of the Earth, and is also trying to do that, trying to use scanning beams. That means uh, it is it could often be some kind of a system which is trying to look for some kind of a disaster management also. That means suppose there has been some information about disaster happening in some region of the earth, so you are not exactly sure about the location. So sometimes under those situations the scanning beams are used in order to locate more accurately the system. And then we can always have this orthogonally polarized beams. That means they could be either vertically polarized or horizontally polarized, and you can increase the number of users that way. This is also a bit similar to the orthogonal polarization frequency reuse technique that we have studied earlier. So typically, as a rule of thumb, it is seen that if the beam width is like around 10 degrees, beam width of the transmitting antenna on board the satellite, then it will cover nearly about more than 6,200 kilometer of the Earth. The coverage diameter will be something like that. And so that's like you can understand that it's almost like half the uh, radius of the earth. Okay, an area that big could be covered if you can achieve a transmitting antenna on board a satellite which is having a beam width of about 10 degrees. If it is reduced to say something like 5.7 degree, then the corresponding diameter will be like 3,576 kilometer. Then 2.8 degree will be about 17 to 1800 kilometer, and 1 degree will be more like very precise or focused beam. So that will cover only about 600 kilometer or so, the earth coverage diameter. Then there are some standard relations which are used in order to calculate that, what in order to understand that what will be the required diameter and gain of a satellite based antenna in order to achieve the desired uh, objective. So we know that an aperture antenna, it will have a gain which is given by this kind of a relation, 4 pi effective aperture, and that effective aperture is once again the product of the antenna aperture efficiency times the physical aperture by lambda square. So this relation is well known to you, and uh, we could also write this expression in terms of the diameter, okay, of the antenna, diameter of the circular aperture of the antenna. Now, The beam width of an antenna, uh, which is usually given in terms of the 3 dB value, the 3 dB beam width in a particular plane, that is related with the wavelength and the dimension or diameter of the antenna through a relation like this. That is theta 3 dB is 75 lambda by d degrees, and this theta 3 dB, this is the beam width between the half power points. That's the 3D. That's by definition is what is known as the 3 dB beam width. And using this kind of a relation, there is also another one that if we put these equations together, which contain the antenna dimension parameters, then we could also write that for antennas with typical aperture efficiency of 60%. Okay, so as I was telling you that not all the incident radiation is reflected back towards the focus of a parabolic reflector. Some portion is lost. So we could see that nearly 40% of the incident radiation is lost, and these are these are issues where we still need a lot of development. Okay, that is, the signals are weak, and even with those weak signals, we are making further losses because of uh, kind of our fault. That means we are not able to design, these reflecting surfaces in such a way that the aperture efficiencies are higher. It's only like 60%. So 40% of the incident radiation is lost. Same thing happens in case of the solar cells. As I have told you that the conversion efficiency is only about 15 to 17% at the beginning of their lifetime, and that decreases as the age of the solar cells increase. So you can have an approximate rule of thumb that the gain will be given by this 33,000 by theta 3 dB square. Okay, so let us just use these equations and work out this relation. That is, can you see this problem? That the Earth subtends an angle of 17 degree when viewed from geostationary orbit. Can you see this?
Yes, sir.
Yes, sir.
So what I would like you to calculate is that the dimension and gain of the horn antenna that will provide global coverage at 4 gigahertz. Okay, so this information is already given to you, so you can very easily calculate that this d by lambda that will be over here, as you can see, that is 75 by theta 3 dB. Okay, from here, from this simple expression, you can see. So just put the values and tell me what will be the dimension and gain of a horn antenna that will provide global coverage at 4 gigahertz, because 4 gigahertz is one of the downlinking frequencies.
Sir, D equals to 0.33 meter at 4 gigahertz.
Yes, sir.
0.33 meter. That means about 33 centimeter, right?
Yes,
So
sir.
Yes, sir.
that means about 1 feet, right? Of diameter.
Yes, sir.
So
One
you are
feet.
saying that if it is a circular dimension, then the diameter will be like 1 feet only. Okay. So that will give you an idea that uh, the satellite may be huge in size. Like when we had seen that video of ISRO launching the geostationary satellite INSAT, one of the INSAT satellites, then we had seen that the size or the dimension of the satellite launching vehicle is huge. The satellite is also quite massive, but when we understand the dimension of the antenna on board the satellite for downlinking the signal at 4 gigahertz, we have now calculated that it's around 1 feet diameter. So that's not a huge structure. And of course, we should remember that each of these vital, you know, installations on board the satellite, they always have backup. That means it is not that the entire communication capacity or capability is dependent on only one such antenna, one such horn antenna having a diameter of 1 feet. There should be at least a few, so that one of them fail, there are others to take up the position. And what's the gain? What is the value of the gain? You can use this
20.57 dB.
20.57 dB. So, by the way, what does this mean? That the gain of anything, say for example, is 20.57 or 20 dB, whatever. What does this mean?
Sir, if we had an isotropic antenna, then whatever the value of the signal, like whatever the strength of the signal we will get at a point, if we will use this antenna instead, it will be greater than that isotropic antenna by that much dB.
See, uh, first of all, satellite communication antennas are never isotropic
Yes.
because they have to receive signals from a particular direction only, uh, at which or towards which the antenna should be pointed. And for that, actually, we have different units. Like for decibel is one thing. You can have dBW. That means how many times it is more or less than 1 watt. That is dBW, dB watt. If it is in milliwatt, we have the unit dBm. Okay, that means there are several units to deal with that. Like for example, uh, you can have the simple dB, of course. Then you can have dBW. You can have dBm for milliwatt. You can have dB mu for microwatt. Where is mu? Yes. dB mu for microwatt. You can have dBp for picowatt. Okay, and dBi, that is for that isotropic thing. Okay, it is not that this value of so many dB. It means with reference to an isotropic antenna. Okay, because satellite antennas are never isotropic, excepting for if time permits, if we get a few classes upon the satellite, some of the medium earth orbiting satellites, then we will see that there are some kind of antennas which does use the isotropic concept. So we have now got the values of these 4 gigahertz downlink. Now, suppose if we switch over to the 11 gigahertz, that is also one of the downlinks at 3 degree half power beam width. So, what will be the corresponding values of this diameter and gain?
So for theta equals to 3 degree.
Yes, 11 gigahertz downlink.
0.68 meter.
How much?
0.68 meters.
0.68.
Yes, sir.
So
0.68 meter.
so that is 68 centimeters. So it's a little more than 2 feet, right? And
Yes.
yes, and the gain.
Sir, it is near to 35 dB.
35 dB. So what about the others? Are you working out these problems or not? Please tell me your names who have given me the answers.
Sir, Moushumi Shau.
Okay,
Stromona Mojumdar.
okay. So what about the others? Whenever I ask this question, like Shayantan Mujumdar left the meeting, Arup Marik leaves the meeting. Okay. Chirantan, have you worked out this problem?
Yes, sir.
Okay. So let's move ahead. Now, the next thing, so we have now discussed about the different subsystems of a communication satellite, starting from the telemetry, starting from the attitude and orbit control system, then the telemetry, tracking, command and monitoring system, then the power subsystem, the communication subsystem, and finally the antennas on board a satellite. So these were the 5 different, classification of a communication satellite, subsystems of a communication satellite. Now, before the launch of a satellite, any kind of satellite, there has to be extensive tests done on those satellites, and various prototype models have to be developed. It could be the mechanical model, there is also a thermal model as well as an electrical model. Now this mechanical model, it contains basically all the structural and mechanical parts. Like for example, during the launch of a satellite, as well as after it is placed in orbit, basically in the geostationary altitude, the satellites are operating in a near vacuum condition. Okay, so uh, while during the launch process as well as during the uh, exit from the Earth's atmosphere, it is subject to huge amount of vibration and shock. Okay, so at the ground, on the ground, in the laboratories, there has to be, simulations of each of these effects. And by simulation, it is not only, computer based simulation. There has to be some chamber within which the moving parts of the satellite has to be put, and that entire chamber has to be subject to uh, vibration and shock levels which are expected during the launch as it moves against gravity, and also during the exit from the earth's atmosphere. So during these two periods of time, huge amounts of vibration and shock they are expected, and so the mechanical model has to be entirely tested on the ground prior to launch of the satellite in order to ensure that they can withstand those levels of vibration and shock. Because in case of a satellite launch, whatever may be the kind of satellite, low earth, medium earth, or communication satellite, so once the satellite is launched, we do not have any further option to do research and development on that particular satellite. We can only expect and hope that it will function properly, and whatever corrections we can from the ground command, we can do those. Okay, from the ground control station. So that is why there has to be extensive tests on the satellite, and for that, these three different kinds of prototype models have to be developed. Then, secondly, so in the mechanical model, you see one of them is that huge amounts of vibration and shock that is expected during the launch, and once it is put in orbit, which is like near vacuum, then uh, whether the moving parts they function properly in vacuum over a wide temperature range or not. So that means on the ground-based uh, testing laboratory, this vacuum condition also has to be simulated and checked thoroughly, that whether these different subsystems they perform at the same level with the same accuracy in vacuum as under normal pressure conditions. Second is the thermal model of the satellite, and this thermal model, essentially it contains all the electronic components and devices. And because we have already learned that for a satellite in orbit, it is subject to huge amount of radiation from the sun, almost like 1.4 kilowatt per square meter, so that the outer surface of the satellite will uh, can achieve temperatures as high as 200 degrees Celsius when exposed to the direct sunlight, and also when it is in the shadow of the earth during the eclipse period, the outside surface temperature could go down to as low as minus 200 degrees Celsius. So that means the electronic components they are uh, passing through a very large temperature cycle. Okay, thermal cycling that is there. So that is why for this thermal model, it has to be once again simulated on the surface of the earth. And very often what is done is that very powerful heaters are used to simulate that amount of radiation from the sun. And the antennas are also included, not only the electronic components, but the antennas are also included in that model, because we have to check that whether any kind of distortion, physical distortion of the reflectors or bending of the support structures they are happening or not. And also whether the antenna beam patterns are dependent on temperature or not. That means when you cycle them from a few hundreds of degrees Celsius to a few hundreds of of negative Celsius, whether over this large temperature range they are functioning as per the specifications or not. Then third is the electrical model, and this electrical model is actually meant, for all the subsystems which are present within the satellite itself, and the amount of current and voltage ratings uh, which are expected to flow or to be maintained across those components, all of them have to be tested under nearly total vacuum and over a wide range of temperature. And usually, what is done is that in all of these three models, uh, the values of vibration maybe, or the gravitational forces, or the temperature range, or the current and the voltage ranges which are expected, usually while testing in the lab, the ranges are specified at least 30 to 40% more than that. Okay, this is just a precautionary step taken so that you know you check your system under most severe stressful condition, so that when actually you have put them in orbit where the conditions are not that severe, maybe compared to what you have tested on the lab, you are more confident that your system, they will endure this very harsh environment at the geostationary altitude. It is a very harsh environment. Okay, and that is why when this kind of manned missions are planned, in addition to all these three things, there also has to be a kind of uh, effect on the humans. Okay, because these mechanical parts and the electronic components, they are some kind of a non-living object. But when it comes to actual humans, there you have to check what are the effects of these nearly vacuum condition, or the severe gravitational forces, the huge temperature changes that are there. Of course, the interior of the satellite is maintained at a particular temperature, so that uh, it is not that the components as well as the astronauts, they are subject to this huge range of temperature. Not that humans cannot sustain that. And also the radiation effects. Okay, because about 40,000 kilometers above the surface of the earth, you are no longer protected from the harmful radiation of the sun. In our case, on the surface of the earth, the ozone layers, they are protecting, or the atmosphere as a whole protect some kind of a, they provide some kind of a protection against the harmful radiation from the sun. But at those altitudes, actually they are not there, and so the amount of radiation to which the astronauts are subject to, they are quite severe. So uh, that is also an added component, a kind of human biosphere tests which are done nowadays in order to understand that whether humans could sustain that kind of an environment or not. So, as I was telling you, that the testing which are carried out on these prototype models, they are usually, kind of overstressed, I should say, the system. That means it is not that the actual values which are expected are put during the simulation uh, tests, but we are putting in at least 30 to 40% more. Okay, and to check, because that will lead us to an understanding that uh, which are the weaker components more subject to failures. And then the temperatures also cycling that is done, as I was telling you, at least 10 degrees or more above the expected extremes. Okay, and the structural loads. Okay, these tests are quite interesting. If uh, you have any opportunity to visit these places to see the structural load tests and also the gravitational forces that are expected. These tests are really, very interesting to watch. Okay, the vibration levels, and during those vibration level tests, one has to. I mean, the personnel, the humans who are testing those systems, they have to put on special jackets, and they have to put on their some kind of a helmet with all their ears and nose covered, kind of a thing. Okay, so it's very interesting but challenging working on these prototype models or testing these uh, prototype models. So, because the space environment is, so much of a hostile one, naturally, I mean, the natural hostility is there, the temperatures are high, and sometimes during eclipse period, you can have, temperatures almost close to absolute zero, and it's vacuum. So all these, uh, put a severe limitation on space qualified components, and as a result, space qualification is a very tough test for any component or subsystem manufacturer to pass. So, the space qualification is necessary, and the space qualification and the space qualified components, they are not readily available. I mean, you cannot go to Chandni market and buy space qualified components. They are manufactured only uh, at one place in India, Bharat Electronics Limited, Bell. And as far as I know, Bell is the one which is providing ISRO with Indian Space Research Organization with all the space qualified components. And the space qualified components, typically uh, they have to have a certain amount of reliability. And when we talk about reliability, it is not something that, okay, it has got a very good reliability or it is not so reliable. I mean, this kind of qualitative analysis won't work. There has to be some kind of a quantification, some kind of a parameter which will tell me exactly that what is the kind of what do I expect from a particular device or a subsystem. Now, when we plot the probability of failure, okay, of any device or component as a function of time, then usually what we note is that at the beginning of its lifetime, there are usually a very very high probability or a very sharp change is expected during the initial part of a particular device. The probability of failure is quite high. That is because of the fact, I mean, that is also our common experience. That is, you simply you simply connect an electric bulb, switch it on, and immediately the fuse blows. So that is the kind of failure which happens very frequently in different kinds of electronic or electrical devices at the initial part of its lifetime, which is known as the burn-in period. Okay, the burn-in period. Then, once the device or the subsystem passes that period, then over the lifetime of that particular device, it is more or less having a nearly uniform probability of failure. And then at the end of its lifetime, because of aging and other related factors, once again the probability of failure it increases. So this is something which we expect at the end of life of a particular uh, device or component. So in case of a satellite, you can understand that this is one cause of worry for the satellite system designers, because during the initial part of the operation of a satellite, if the failure happens in some of the vital components, then the satellite mission itself that could be in jeopardy. And also near the end of its lifetime, there is, due to aging or other things, once again a high probability of failure. Now, this is something which you cannot avoid. Okay, uh, you cannot avoid this burn-in period also, but this is something which you cannot do anything other than expect that the probability of failure or the active lifetime of the satellite is extended as much as possible, where you have this nearly uniform or constant probability of failure. Now, in order to bypass this initial burn-in period, what is done in case of satellites is that, knowing fully well that once the satellite is launched, the possibilities or or the option of any kind of repair and rectification of any component is not there once the satellite is launched. So this initial burning period, if we could uh, turn on the power to all the subsystems of a satellite before it is launched, so that this initial burning period is passed or expired while the satellite is still on the surface of the earth before launch. This initial burn-in period could be like maybe 100 hours or maybe 120 hours. Okay, so this is a strategy which is followed, that you turn on the power to your satellite-based subsystems maybe 120 hours before launch. Okay, that is about 5 days before launch, so that if any of the components they do suffer any kind of burning, then that happens while the satellite is still on the surface of the earth, and you have a provision to repair or replace. It's not repair, it's mostly replace that faulty component or that uh, particular device which has failed. So that way you can reduce the possibilities of the high probability of failure during burning period in case of satellites by turning on all the subsystems. Let the entire system be powered on, so that if any failure happens in any of the subsystems or components, that happens while the satellite is still on the surface of the earth, and we still have some option of replacing that faulty component. So when the satellite is finally launched after that burn-in period, it is expected to have, I mean, the devices and subsystems are expected to have a nearly, constant lifetime over the entire, period of performance of the satellite. And of course, this end of lifetime probability of failure that will be there. We cannot do anything about it, and other than hope that this end of life or aging happens at after the the revenues generated have been significant, and also the work that was supposed to be done by that satellite is complete. Now, talking about the reliability or quantifying the reliability, the definition that is usually followed is that uh, it is the ratio of the number of components which are surviving, that means which have not failed at a particular time t, at a particular instant of time t, divided by the number of components at the start of the test period. That means You might have started with a number like capital N, number of components at the start of test period t equal to 0, and after a finite time interval, which could be like several hours or a few hundreds of hours also, you are testing the number of surviving components or the number of components which are still functioning properly, and you take the ratio of that, and that will tell you the reliability of that particular device or subsystem. Then there are also, other definitions like the mean time before failure. Okay, which is kind of defined as the summation of all these TI, where TI is the time that the ith device fails. So you take the values of all these TI for all the devices from 1 to n naught, and you divide that by the number of devices n naught. So that will give you some idea about the mean time before failure. Okay, that means suppose you find that, okay, my fifth device is failing, is found to have a mean time before failure of so many hours or so. So one thing that we are familiar with is the fact that the high power devices, they are more prone to failure. Okay, so typically about you can expect a mean time before failure of 50,000 hours, which is close to like 6 hours, 6 years of continuous operation of a satellite that is commonly used. That is commonly, the kind of uh, value of MTBF that we expect. And thirdly, other than calculating the reliability and the mean time before failure, and then also ensuring that the burn-in period of the satellite components and subsystems are spent on the surface of the Earth, one should also have enough redundancy. That means enough number of options. That means there should be, the devices for which we know they have a limited lifetime, and also, if we identify that these are the components whose failure will eventually lead to the failure of the entire satellite. So usually we should try to put more number of such critical components or devices either in series, parallel, or any other hybrid connection, so that if one of them fail, at least we have other such units, similar units, to provide the backup. So that will ensure that, eventually, even after the burning period has expired on the surface of the Earth, the reliability of the satellite, of the different subsystems on board the satellite has been calculated, and the mean time before failure, that has also been calculated. Until and unless we have redundancy for, the more critical components in a satellite, uh, your satellite mission, which is expected to cover at least 6 to 8 years, or nowadays even 10 years of active operation, so that cannot be achieved. So these are some of the very important steps which are taken to ensure that your satellite, along with the subsystems and components, they survive the harsh environment of the outer space. I think I will stop here today and continue in the next class. So let me have your attendance now. 301,
Present, sir.
302,
Present, sir.
303,
Present, sir.
305,
Present, sir.
306,
Present, sir.
308,
Present, sir.
309,
Present, sir.
311,
Present, sir.
313,
Present, sir.
314,
Present, sir.
315,
Present, sir.
316, 317, 'What is the name of 317? Do any one of you know? Okay. 318. 318, has he left? Because after the first class, huh? Acha. Okay. 319,
Present, sir.
320,
Present, sir.
321,
Present, sir.
322, 323,
Present, sir.
401,
Present, sir.
402,
Present, sir.
405,
Yes, sir.
407, 408, 411,
Present, sir.
414, 420,
Present, sir.
421,
Present, sir.
422,
Present, sir.
423,
Present, sir.
424, 430,
Yes, sir.
431,
Yes, sir.
432,
Yes, sir.
433, 435, 435. Who is 435? Do you know his name? Four three five.
So just a minute, I have the names I'm telling you. So it's Ram Pravesh Kumar Gupta.
Okay, because he has attended maybe one or two classes. One only. 1 or 2 classes. After that, for the last 4 classes, he is absent.
Sir, I saw he was present today. He is present. I can see him in the class.
But no, he is not responding.
Yeah, yes, sir.
So what can I do? 436.
Present, sir.
437.
Present, sir.
438.
Present, sir.
439.
Yes, sir.
440.
Yes, sir.
441. 442.
Present, sir.
Shayan Datta.
Present, sir.
Ravi Kumar Thakur.
Present, sir.
Okay. So the next class will be on Wednesday. Okay.
Yes, sir.
Okay. Thank you.
Thank you, sir.
Thank you, sir.